Hello, let's begin with a question. Why do we care about efficient spice simulations for bandband CDR verification? On the left, we have behavior simulations using variability, Python, or MATLAB. They are fast, intuitive, and great for tracking algorithms over bandband PD logic. These models are quick to evaluate, align, early and late sampling decisions. But on the right, we have spice simulations like HSpice, Spectre, or Addo. These go much deeper. They model real transistors level effects like mismatch, parasitic, and noise. They reflect what really happens in silicon. So our goal today is to combine the speed of a behavior simulation with the accuracy of spice. Let's look at how we can make spice simulation more efficient while preserving important effects like jitter, ISI, equalization, and loop latency. Let's start with the first change, Bignist. Simulating a full bandband CDR in spice involves many interconnected flags, from TXFV to CTOE, DFE, CDR, and even digital adaptation engines. It's a large circuit. Each added block increases overall size and complexity. Now, here's the issue. Spice is time domain and works at transistor level. It has to compute every voltage and current at every node for every time step. So, as the analysis grows, simulation time increases rapidly, often non-linearly. For example, 5x more block might lead to 50x more simulation time. This often results in overnight runs, or worse, multi-day simulations. If the sims crash near the end, all the time is wasted. So, to summarize, larger analysis means longer sims, harder debug, and less productivity. Let's now move on to the next change, timescale mismatch in CDR systems. Now, let's talk about the timescale involved. Even in just the CDR, CDRs operate over a massive range of time, from femtoseconds to microseconds. Let's break it down. Jitter requirements can be in the hundreds of femtoseconds. Bitrate range from tens of picoseconds to a few nanoseconds per bit. Then we have AC coupling, which introduces time constraint or time constant in microseconds. And the PL, lag time can stretch out to 50 microseconds or more. This creates a huge simulation challenge. You need very fine resolutions to catch jitter, but a long window to see the settling. Simulators struggle with this because zooming in loses the long-term view, and zoom out misses jitter detail. This is what we mean by simulations spanning 100 billions to 1 in time scale. Most simulators are not built for this. So, how do we address that? Let's look at techniques that help us balance both resolution and duration. Let's now talk about why this balance between speed and accuracy matters. Behavior models like Python or variability simulate quickly. They are great for testing ideas, but not reliable under non-ideal conditions. Spice simulations are slow but extremely accurate. They capture all real-world effects, but take time, that's of it. Now, bandband CDRs are highly nonlinear. They are very sensitive to jitter, ISI, and loop latency. So, if we want to understand real behavior, Especially under stress, we need spice level accuracy. Python simulations are helpful, like the Jitter maps on the left, but they don't reflect how the real clock reacts to ISI and latency. Look at the spice plot on the right. Each latency settling causes different clock swings. You cannot get the accuracy from the behavior tool alone. So again, we want smart method that give us spice level realism without simulation time pain. Let's explore how we do that, starting fast frequency locking. Let's talk about a clever way to speed up locking. The VLGA frequency loop. The technique replaces the slow spice PO lock mechanism. Instead of taking microsecond, it can lock in nanosecond. That's 1,000 times per faster. How? VLGA monitor edge count, not phase error, to adjust the control voltage. So rather than modeling the full lock counter in spice, we just track rising edge over time. If the frequency is off, we adjust the V control to clear it. This method enables fast, stable locking, even with PVT or mismatch variations. It's perfect for pre-layout validation and design sweeps. So now we know that works. Let's take a look at what's actually happening inside the servo loop. Here's how VLGA frequency servo works. We start with V control, the control voltage for the VCO. The servo monitors frequency error. If the VCO is too fast, we pull V control down. If it's too slow, we push it up. It's edge counting based, not phase based. Key settings include edge weight, edge sample, and V init. This defines how we sample, how many edges we check, and where we start. Once the frequency is within a tolerance, say plus minus 3% or 1%, we trigger a lock signal. On the plot, you can see the frequency ramping to target and the control voltage settling. When the green lock line rises, the system knows we are good to go. This approach is precise, even for nonlinear CDR loops or band behavior. It avoids slow settling and fast locking. Now that the frequency locking is handled, let's look at how we adjust realistic jitter into the CDR input. To test CDR under jitter, we need realistic stress patterns. We use the simulator's built-in PRBS generator as a voltage source. It's simple to use. Just write a line of code with your settings. You can inject sinusoidal jitter using PJ type sign. Random jitter is handled with RJRMS and RJSeed. Duty cycle distortion is added with DCD. These effects all get added directly into the input waveform, where the CDR samples data. This makes the task realistic and comprehensive. The method mirrors what the compliance standard used for jitter testing. No waveform files needed. Everything is built-in spice. Now, let's move on how we model channel distortion like ISI or over-equalization using Laplace domain filters. Next, we model ISI and equalization using Laplace filters in Spectre IF. We use VCVS components, voltage control voltage source, with Laplace syntax. To model residual ISI, we use a simple low-pass filter. The high-frequency low-off simulates a loss channel. To model over equalization or peaking, we use a high-pass filter with a peaking profile. This lets us create waveform distortion that mimics overboost the CTOE response. Both setups use just a line of code. You don't have to reroute or touch layout. Just change a pole or zero. This gives us a full control over waveform slope and amplitude distortion. We can now stress the band PD with messy inputs, just like what a real sequence sees. Let's now see how we model internal loop latency using similar VCVS methods. Latency is critical in CDR. It affects stability and jitter. We use the VCVS block to model pipeline delay inside the loop. You place them on the early and late patterns of the phase detector. We define delay using a TD parameter, which is latency times T bits. You can sweep this from 2UI to 18UI. It helps explore how latency affects locking and jitter. If a loop becomes unstable or humped, we'll see clearly. And this method is modular. You can combine it with PRBS stimulus and Laplace filter that gives you a full verification setup with jitter, ISI, equalization, and latency all included. Now, let's put all these techniques together in one unified framework. Now, it's time to bring everything together. We use the Variable A Servo for fast frequency locking. We injected jitter using PRBS, both sinusoidal and random. We stimulate distortion using the Laplace domain filters for ISI and equalization. We model pipeline delay using VCVS latency blocks. Each component is modular and easy to tweak. Together, they form a fast, accurate, and scalable simulation setup. And this setup has been validated against the full transistor level simulations. It's perfect for corner sweeps, Monte Carlo, or debug. You can dip inside without waiting days for results. This is how we enable fast, practical band CDR verification. Let's close out with a quick summary. Here are the summarized images showing you what you need efficient spice simulations technique for band CDR verification. There are a few efficient tricks to accelerate CDR development. For example, Variable A gives us nanosecond level frequency locking. PRBS makes jitter stress testing easy and flexible. Laplace filters model channel distortion with clean tuning. VCVS gives precise control over latency. When combined, these techniques give us a powerful simulation platform. It's fast, accurate, and modular, ideal for verifying band CDR across all PVT corners. Efficient simulation isn't just nice, it's essential for modern CDR design or even top-level studies. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video with the people who may be benefiting.